Second law, thermodynamics and heat engines. So, heat engine. So, heat naturally goes from hot to cold, right? Okay. This is actually the second law of thermodynamics. That heat naturally, we've stated it a bunch. We just never really give it a name tag of like, hey, I'm second law of thermodynamics. Heat naturally goes from hot to cold. So a heat engine goes, you know what? There's flow of energy going here. I wonder if we could tap into some of that. Like, is there a way to like harness some of that energy and do something with it? Okay. So that's at the heart of a heat engine. So this is something that uses some of the heat energy that flows from hot to cold and does work. Okay. Something that uses some of the heat energy that flows from hot to cold and does work. Okay. An example of that would be your car engine, which we'll talk about in a little bit. Cool with that? So this is a simple model of a heat engine. It looks at the energy flow. So the red is going to be a hot reservoir. Cold is a cold, or the blue is a cold reservoir. The reservoir is this idea that it's always hot. So it has the same feel of like if I took 5 gallons of water out of the ocean, I didn't just lower the sea level because of that. Or if I dump 5 gallons into the ocean, it doesn't change the sea level. It's this idea that you can add or take away stuff and it's really not going to do much in the grand scheme of things. Okay. So here's your engine. So TH, this is going to be your temperature of your hot reservoir. QH is the heat coming from the hot reservoir. So this is your QH. So as that heat comes, the heat engine's using some of that to do work. So this is the work done by the engine. And then QC. This is the heat exhausted. Unused heat energy. that is dumped into the cold reservoir. And Tc, this is the temperature of the cold reservoir. And this looks at the energy flow going through that. Okay. So as some of this goes, it splits. So we can get a mathematical relationship here of QH is equal to work out plus QC. And when doing this equation, we're going to ignore the positive and negative signs that you learned yesterday for this equation. So does this equation make sense in terms of this energy diagram? This is the source. Some of us go into doing work, others is exhausted into the cold reservoir. So when we talk about engines, another key concept is efficiency. You probably heard that before. Okay. So this idea of efficiency is how much work are you able to do compared to how much energy did you put into it? Like what's the percentage of energy that I was able to do something with compared to what I put into it? Yes. Yep. It is. Good at that. And we can combine this equation and this to say this. QH minus QC, that's work out, is equal to Q sub H. And then the last equation has to do with an ideal engine, like what is the maximum efficiency you could have if you had everything was perfect, no friction, no air resistance, all that stuff. Maximum efficiency is equal to the temperature of the hot minus temperature of the cold over the temperature of the hot. And the temperatures must be in Kelvin to do that equation, which I'll give it to you in Kelvin. You will not need to convert, just letting you know. In case you take another thermodynamics class at some point in your lifetime, or not. Cool with that? Thumbs up when you are ready for that slide to go away. All right, here we go. Oh, I told you this. Second law of thermodynamics, heat naturally goes out of hot to cold. Okay. Oops, not that button. All right. Tell your neighbor. Correct answer is A. This is the source. It's where it's coming from. Okay. All right. So one example of a heat engine is a steam engine. Okay. So reference all the movies that you've seen of like westerns or anything with a steam engine. Okay. So the system is going to be the water molecules. Okay. In your movies, what's the first car behind the engine? Coal car, or sometimes as wood. Why do we need coal? You can burn it. Okay. So the fire, this is our hot reservoir. Okay. That temperature does not change. Why? Because we keep feeding fuel to the fire. You all right with that? Okay. That's our hot reservoir. Now our cold reservoir, that's going to be the outside environment. So if you burnt coal, heat would naturally go from the hot fire out to the atmosphere, to the cold reservoir. Does that make sense? Like that just happens naturally if you burn something. What a heat engine does is like, you know what? There's energy that has the ability, like we could do something with that. We could capitalize on it, harness that energy somehow, some way. And so one example of that is a steam engine. Okay. So we are going to take heat and put it into going from the hot to the colder water, warming that up, boiling that really. Good with that? Now, as that boils, creates steam, that steam becomes pressurized, and there's a movable piston here. So the boiler is this thing, the big part on the train, like think Polar Express, like that big cylinder thing in the front, that's a boiler, it holds water. We're heating that up right by the fire. You okay with that? Okay. Now, that steam pushes on this piston and expands. We're doing positive or negative work here. We're doing something. Dun, dun, dun. Okay. Why do we care? Those pistons are connected to the wheels. Okay. Does that make sense? And then once it gets to a certain point, the steam depressurizes and goes over here to a condenser. Okay. Where some of it is released straight away. Smokestack. Okay. Some of it goes through a condenser. We don't really see that. And heat leaves exhausted out into the environment. You okay with that? And that condenser cools it off as heat leaves, goes from the hot water, steam to the outside environment, cools that off, condenses it back to water, and then they pump that back into the boiler. And it's a fairly closed system. You get some of it, the water molecules leave. Most of them stay in there. And every once in a while, after you go across country, you fill it back up, top it off with water. Right.
What do they use as a pump to put
it? Pump? I don't know. I mean, we've had pumps for a long time. So it would be driven, I would assume, by the wheels. Like you connect that to the wheels and you just kind of pump that in there. Okay. But as this goes, it's like, but it's getting the next one ready. And we're moving. That makes sense? Okay. So one of the characteristics of an engine is it has to be repeatable. That process has to be repeatable. Okay. So this first question, why are you doing that? There you go. This first question has to do with this process right here. My suggestion would be try to figure out one of those variables and make them 0. Tell your neighbor which variable is 0. What's 0? Work is 0. No change in volume. Okay. Again, I'm just focusing on this process here. So what's hotter, the system or the environment? And the environment in this case is fire. So this environment's hotter. Yeah, with that. Okay. So work is 0. We're adding heat. Therefore, we're increasing the internal energy. We're making the water hotter, making it into steam. You all right with that? So, B, babbling baboons. Okay. Next process is looking at this, just this part here. Try to figure out which of these three is going to be 0. Tell your neighbor what you think. Hint. What is 0? Heat. How do you know? If it goes quick, it's like, whoa. Heat doesn't have a chance to go from hot to cold. It's like, oh, I want to get there, but I can't. Okay. So, heat 0. Correct answer is A. What does this mean? This is positive. It's doing work. Where did that energy come from in order to enable it to do positive work? It didn't come from the outside environment, so it had to come from inside, within. It came from internal energy, making that steam cooler. It's still hot steam, but it's not as hot as it was before it was expanded. That makes sense? Kind of did the aerosol can thing, but we actually did something with it. We didn't make it like cold, we just made it not as hot. Good? And then the last question is going to be focused on the condensing part, the condenser part. Thumbs up when you have a guess. Thumbs up if you're playing along. Have a conversation. Correct answer is nicely done. C, Crazy Cats. Okay, so that's 0, no change in volume. The system is hotter than the outside environment. So we're losing heat, causing temperature to decrease. Good? Okay, let's bring it to an example that's a little more applicable to life. That would be the engine in your car. Okay. So this is, have you ever heard of the expression like V8, V6, inline six, four banger? Okay. That's talking about how many cylinders in your engine, how many pistons in your engine. Okay. This is one piston going through the 4 stages, the 4 cycles, the 4 phases. I mean, you can call it a lot of different things. It's a 4-cycle engine. Okay.
First, intake stroke. The inlet valve is opened, and the fuel-air mixture is drawn in as the piston travels down. Second, compression stroke. The inlet valve is closed, and the piston travels back up the cylinder, compressing the fuel-air mixture. Just before piston reaches the top of its compression stroke, a spark plug emits a spark to combust the fuel-air mixture. Third, combustion stroke. The piston is now forced down by the pressure wave of the combustion of the fuel-air mixture. The engine's power is derived from this cycle. Fourth, exhaust stroke. The exhaust valve is opened, and the piston travels back up, expelling the exhaust gases through the exhaust valve. At the top of the stroke, the exhaust valve is closed. This process is repeated. What had been presented is the cycle of operation of one cylinder of a 4-stroke engine. Generally, engines have 2 or more cylinders acting in concert with each other to produce the engine power.
Okay. So, all right. Have you played with a syringe, like squirting water? Okay. This part here is like sucking water into the syringe. Okay. It's sucking in the fuel air mixture. It's kind of like a mist or a vapor. Okay. Then that's closed off, and the piston comes up and compresses. Okay. And it does this. Okay. That. Okay. Now, on a diesel engine, this compression gets the fuel, the diesel fuel, hot enough to ignite by itself, just like we saw yesterday. Okay. Except when it gets really cold out, and the compression doesn't get it hot enough, that's why it's hard for school buses to start. So you need a glow plug, something to warm up the engine on cold days to get it to go. On normal gasoline engines, this is not hot enough to ignite the gasoline. So you have what's called, or like a spark plug. Heard of that? Okay. That helps, that makes it ignite. So it's hot, but then to like ignite it, spark plug goes, and then boom. This is the power stroke. This is what, now you're doing positive or negative work here. Is the system doing positive or negative work? Positive. Or expanding. This is what drives your car. Okay. This is the hot reservoir doing work. And then on the return stroke, it opens up in a valve and it squirts out the exhaust that goes out your tailpipe to the environment, cold reservoir. All right with that? Okay. So do you know, okay, some of you in your car have the gauge. You know what I'm talking about? Okay. It's called a tachometer. And that measures what? RPMs, rotations per minute, times 1,000. Okay. So let's say you're going 80 miles an hour down the interstate and your tachometer says 3. That is 3,000 rotations per minute. To figure out how many rotations per second, divide that by 60. That is 50 cycles for every 1 Mississippi. Like just going nuts. Like this is like, rah. Okay, do you see where your gas goes? Okay, go with that. So here, it starts on the power stroke. Boom. We call that combustion, not explosions. Squishes out the exhaust, draws the fuel in, compresses, spark plug, ignition. Pushes out the exhaust. Crazy. Good at that? Okay. All right. I'm just going to leave this. Cars fall in this category here. Okay. So let's say it's 25% efficient. When you go to the gas station and you spend $40 filling up your tank, only $10 goes to getting you from point A to point B. $30 goes to warming up the environment. Well, I drive an electric car. Oh, good for you. Where do you get that electricity from? The battery. Well, yeah. Well, what'd you plug that into? The outlet. So that just magically gives me energy. Where does the outlet get its energy from? Electricity from? Generators in the electric company that burn coal and uses a heat engine to spin. Oh, and let's not talk about the battery once it gets done with its life. And you can just throw that in the landfill. I'm sure that's great for all the live environment. Now, electric cars are a tad bit more efficient, but not much. Like generators and a power company are a little more efficient, but like grand scheme of things, if you're enjoying the amenities and the comforts of first world society, you're killing the planet just like everybody else. Not to say you should just like go out and like burn coal just for kicks and giggles, but like big picture, not looking pretty. If you want to do something good, like buy a horse. Carter.
Is the gas that's being addressed? Where does it go?
Where is it? It's from your gasoline tank. So it's like it's shooting like a mister bottle, like if you're like cleaning windows, like okay, so it's spraying in like a fine mist of fuel and air every compression. Like it's drawn in the mist, compresses, bang, spits it out, sucks it in, but from the gas tank.
What's the very first step of the diagram?
It's drawing it in. So this is the gas tank's over here somewhere. So it's drawing that in. What brings what? Oh, good question. So you need a starter on your engine at the beginning. So, and that's an electric motor. So when you're trying to start your car on a cold morning and your battery's dead, or it doesn't, it's like it's not producing chemical reaction as quickly, that's why it's a struggle to start. Once the electric motor gets it going, then it's self-sustaining. But it needs that. Remember in old movies where like the guy got out and like was cranking on the car, or like propeller movies, and they're like something needs to start that off. Now we have electric starters, which is a motor that runs off your battery, gets it going. That's why you don't want to do the ignition switch after the car is started. I don't know if you've ever done that before. You get this like grinding, like the engine's already going and you're engaging the starter, and it's bad. Don't do that. Good with that? Great question. Yep, got a worksheet.